Okay, so that's our second quantum number is L. Now we need to move to the third quantum number, which is m sub L, the magnetic momentum quantum number. So these quantum numbers have a subscript because there's multiple quantum numbers that are called m. So m sub L is the magnetic quantum number. Its value is going to be an integer like the first two, and its potential values are between negative L and positive L. So this is the first one we've seen that can have a negative number as its value. And we use m sub L to tell us about the orbital, which gives us information about the orientation of the orbital. So let's talk about how to calculate the number first, all the possible values. So our m sub L values start at negative L and increase to the next integer until they get to positive L. So if we give an example, if L is equal to 0, which is the smallest value for L, then our values for m sub L are from negative 0 to positive 0, which we know is just 0. So for s orbitals, there's only going to be one possible orientation of that type of orbital. If our L value equals 1, which is the next largest option, then we have a couple of options for m sub L. We can go from negative 1 up by integers up to positive 1. So our m sub L could be negative 1, or it could be 0, or it could be positive 1. And so on and so forth as we increase the L values. So this is how we figure out what the possible values for m sub L are. And these are going to tell us about the possible orientations of the shape we talked about up here. Oh, and it looks like we forgot to label them. Let's go back and label them just to be complete. So if n equals 1 and L equals 0, we would call this the 1s orbital. If n equals 2 and L equals 0, it's the 2s orbital. And n equals 3, L equals 0 is the 3s orbital. And then L equals 1, we called P, so this would be 2P, and the next one would be 3P. And our L equals 2, we called D, so this would be 3D. So this is sort of a more pleasant thing to look at, a letter and a number, or a number and a letter, rather than two numbers in a row. And each of these types of orbitals comes in several different flavors or orientations, and that's what these m sub L values indicate. So let's make this table for L again, and this time we'll show the different flavors of each of those shapes. So our values for L are 0, 1, 2, and we won't go to 3 because drawing the pictures is just horrendous. We call those S, P, D, and F. And they also are going to have the other type of node that we briefly mentioned in the last video. They're going to have angular nodes. And the number of angular nodes is equal to the angular quantum number. So that's pretty easy to remember. So there's going to be 0 angular nodes in this one. There's going to be 1 angular node in a p orbital, and there'll be 2 angular nodes in a d orbital. And I'll show you what that looks like in the picture. So we said L equals 0 is an s orbital. S orbitals look like a sphere. So I can draw that. That looks like a circle. When we have the p orbitals look like a dumbbell. kind of like two balloons tied together. And according to our calculations, if L equals 1 and we're talking about a p orbital, there are 3 different values for m sub L, -1, 0, and +1. And if there are 3 different values for m sub L, that means that there are 3 different possible orientations for this orbital. And that's what we meant up here, 3 orbitals that look like p. And the way we can tell them apart is we can lay these orbitals on different axes. So one of those p orbitals sits on the x-axis, one of them sits on the y-axis, and one of them sits on the z-axis. So if we wanted to label them and tell them apart, we call them px, py, and pz. You may be wondering, why don't we just call them p sub -1? Why don't we put the m sub L number in there? And that's because the m sub L number gets a little bit complicated and doesn't necessarily correspond to just one picture. So we name them based on their location on the Cartesian plane. And let's see. So the d orbitals, we said that there were 5 different flavors of d orbitals because there's 5 values of m sub L. We could have -2, -1, 0, +1, and +2. And we said the d orbitals looked kind of like a 4-leaf clover, like they were 2 p orbitals combined. And the way that some of the d orbitals look, it's easiest to draw it if you draw the x and y axes, and then you draw the lobes sitting in between them. This works for 3 of the d orbitals. So we've got 3 of them that look like this. You will get used to drawing these quickly as we practice talking about them. So same shape, different axis. This one's on the x and z axis. Same shape, different axis. This one is between the y and z. So these 3 d orbitals all look really similar to each other. They have the same 4-leaf clover shape with the orbitals lying in between 2 of the axes. The next d orbital, the 4th one, looks very similar. It has that same 4-leaf clover shape, but this time each of the lobes lies on top of an axis. Specifically the x and y axes. This one is a special one. And then our last d orbital is the strangest looking one of all. It looks kind of like a p orbital that is inside of a hula hoop or a donut, where the p orbital part is sitting on top of the z-axis, and the hula hoop or donut part is on the x and y axis. So you'll have some practice drawing these, but these each have names based on the axes that they're sitting on. So this one is called dxy, this one is the dxz, and this one is the dyz. Then we can't name this 4th one dxy because we already have a dxy, and they're both on the same axis. So this one is dx squared minus y squared for quantum mechanical reasons. And this one, the p orbital on the z-axis with the hula hoop, we call that dz squared. So there's 5 different flavors of those d orbitals. Now let's take a closer look at a better looking drawing so you can see what those are supposed to look like. This is another picture taken out of your textbook. So these are pictures of the different orbitals. So up here at the top, we've got our L equals 0. Oop, that's not the color I wanted to use. L equals 0, which is going to be our s orbital. That's the one that looks like a sphere. That one is going to have 0 angular nodes. I was too afraid to draw the angular nodes on my picture on paper because I was afraid it would be completely unreadable Okay, and then this next set, these are the p orbitals, where L is equal to 1. And there is going to be one angular node in each of these shapes. So remember, a node is an area where there is a 0% chance of finding an electron. And so you can usually see it if you look close enough at the picture. So the node is going to be between each orbital lobe. We are actually going to add that to our sheet because that's important. So the angular nodes are between orbital lobes. And the lobe is one of the balloons. If you could picture there being a gap between two balloons, that's an angular node. All right, so let's try and find them. You can see here in these pictures, these p orbitals look like they're made of two balloons. And so in between each of the balloons is a gap. And that gap looks like a line in this case. And where there's a line, there is an angular node. All right, then our next set is going to be L equals 2. Those are the d orbitals. Those are these 5 along the middle. And each of these d orbitals has 2 angular nodes. So an angular node is going to be a vertical line, some sort of a plane through the molecule in between nodes. So you can see them if you look. It's especially easy for some of these where the nodes sit outside of the axes, right where the axes go through these first 3. Those are the nodes. In this picture, they're here and here. That one is weird. We're going to skip that one. And in this one, they're here and here. So those are our X, Y, X, Z, and Y, Z, the ones that sit just off the axes. This one over here, this is the X squared minus Y squared that sits on top of the axis. And in this case, our nodes look like this. The nodes are the ones that aren't on the axis this time. And over here in our dz squared p orbital with a donut, they are X-shaped nodes. And then all these interesting, wonderful 6-lobed pictures at the bottom, those are the L equals 3 F orbitals. And those are far too exciting for me to make an attempt to draw. And we won't talk about them much, but they're here if you're interested. And if you're feeling particularly awesome, you can try and find the 3 angular nodes in each of these F orbitals. They are planes you can pass through the molecule that separate 2 different nodes. Okay, that's quite enough fun for one day. Let's summarize what we know about M sub L. So electrons with the same N and L and M sub L values have the same energy, just like before. And they have the same location. So remember when we said that the 2 electrons live inside each orbital? If these orbitals have the same N, L, and M values, they are living in the same orbital. So they're living in one of these pictures. To go back to our analogy of the street address, if 2 people had the same N and L and M sub L values, this is like 2 people that live on the same street. It is getting kind of freaky. You kind of don't want to know where that person lives because all of a sudden they live right in your backyard. You are living in almost the exact same location. So that was the second quantum number L and the third quantum number M sub L. We have one quantum number left, and that's M sub S.